Now for the third and last issue. Some say issue, some say issue. I don't know how to say. I found that Roger Penrose himself, maestro, shortly, been given the Nobel Prize, very famous physicist. He says issue. Possibly this is the British English pronunciation. I never heard it before. Most people say issue, I don't know. Okay, so, but this will be the most complicated part, of course, and it's also very abstract, I must say, since the newly found rotation field of F, which is relatively interesting, a little bit looks like a vortex field itself. You remember? It was this one. Vortex field, because there's a certain perturbation, you could say, of the components here. So knowing what the rotation is, sort of like this, it is to be expected that still even the rotation of F has a rotation itself. But this is very abstract to interpret. Well, and also the divergence of it should be taken. Now let's do so. Looking here, well, the divergence of rot F, in other words, the divergence, of capital R, how we called it, here it is quite simply to be calculated, because in general, it's very simple to calculate the divergence. Just take the first component, differentiate for X, the second partially for Y, the third partially for Z. So, and that's it. Look, this does not depend on X. This does not depend on Y. This does not depend on Z. So there's nothing. We get 0 plus 0 plus 0. It's still a scalar the field that we get, but actually it is 0. And this time we can say, I should perhaps do it. It's even identical to 0. Now, you know what I mean. It's 0 everywhere. It's just a null field, a null scalar field. I may even notate it again, null field. But remember, the null fields, the scalar null field is just a 0, while the vectorial or the vector null field is, of course, a null vector. That's an important detail. But anyway, they both disappear. So what do we find? We find that the rotation of our vector field itself as a field has no divergence. And of course, this is not a proof at all given here, but it's a proven fact that always the divergence of a rotation field equals 0. So you could say it's a very deep and important feature of vortex fields, that their description with the help of a rotation field, which, remember, it describes the direction and strength of vorticity inside the original field, that this abstract representation of the vorticity of a vortex field does not have any sort of radiality. That's what you can say. Here, read. A field describing the vorticity of a vortex field, it needn't be a pure vortex field, but a field with some vorticity. This field describing the vorticity of a vortex field has no radiality. It has no flux outside of a closed surface. As abstract as it sounds, as abstract it is. So I can't tell you fairy tales now. It's just as it is, but it's interesting. Okay, and the next is even perhaps even more interesting. The rotation of F. So rotation of capital R vector field. Let's just take it. It's all the same procedure again, but now of course applied to vector field R. So let's look and see. The third for Y, I just short way of speaking now, okay? The third for Y minus the second for Z. Let's look here. That's it. The third for Y minus the second for Z. Is that right? It seems, because this one differentiated for Y equals 1. This one differentiated for Z equals -1. And so we get 1 minus negative 1. It's interesting. It's 1 minus negative 1, which is 2, constantly 2. And actually that's all, because the first for z minus the third for x, look here, first for z, no dependence. What did I say? The third for it? No, sorry. Yeah, the first for z, the third for x. Third does not depend on x. So there's nothing else. This is 0 minus 0 is 0. Here, second for x minus first for y. No dependence on x. I can't remember it. Second for x, 1 for y. The second does not depend on x. The first does not depend on y. So there's no contribution at all. So this, it's not a surprise that the field, which has a 0x component, while the other components are in general non-zero, has a rotation where it's the other way around. That's typical, okay? You can remember. It's typical that then the first component gets non-zero and the other two get 0 for the rotation of this field. Because what does the rotation of f describe? Well, it describes the way in which vortices of the rotation field are oriented. And since this is a field, look, this R, capital R field, whatever it represents, has the feature that it has no, well, let's call it, what's the x component? In the visualization, it's most often it's the front and back direction. So it has no front back components. All these vectors, you could say, if I draw it, they are all parallel to the drawing area. And now, if there is vorticity, where does the axis of vorticity point? The axis of any vortex point, if I have a vortex here, look at my cursor. A vortex in the plane here will have an axis of rotation which points towards you, or either or away from you. So, and this is in the typical visualization, this is the direction of the x-axis. So that's why the rotation must have a non-zero first component and 0 second and third. That's no surprise at all. It's neither a surprise that we have a non-zero rotation of R. So it's simple. And interestingly, this is a constant field, which means it's a homogeneous field even. Very simple. Now, as a little, let's say, conclusion or abstract of all the things we've been doing, summarizing, just for you now for a second. What does the gradient do? The gradient transforms a scalar field to a vector field. The divergence operator converts, you could say, or transforms a vector field to a scalar field, because divergence is a scalar property. Thirdly, rotation as an operator transforms a vector field to still another vector field. So in a sense, this is the most complicated situation because you have to imagine two different vector fields. And in general, a vector field is a little, well, it holds a little more or definitely more information than a scalar field. So this is quite clearly the most complicated case. But now, and this is also, I pull it out of thin air, okay? But it's a fact that in general, the rotation of F can also be expressed as to be, now it's interesting, the gradient of the divergence of the same field F, but as you could say as a correction term, minus delta vector of F. And now I hope Martin at least introduced it. I think he did. This is still another symbolic operator. It looks so harmless, but I can tell you it's full of power and it has a very prominent name. It's the so-called Laplace operator. Actually, this is an abbreviation, another abbreviation of taking the nabla operation squared. So if you remember that the nabla vector is sort of a pseudo vector containing here the partial derivatives for x, for y, for z. Now it's taken times itself beforehand. Times itself means by using a scalar product. And so what happens is I get something differentiated for x times something differentiated for x. So this unknown something will be differentiated for x, partial derivative for x, even twice. So whatever gets there, it will be differentiated, partial derivative will be taken for x and again for x. So we notate this. This is the modern way of notation, you know. So we notate it with an index xx. And plus, because I sum it up, whatever gets here gets differentiated twice for y, and plus whatever gets here gets differentiated twice for z. That's what Laplace operator does, and it's very important and prominent. Why? Well, first of all, because it's contained in the famous Schrödinger equation describing the world of quantum mechanics. As you know, still one of the most fundamental equations of physics all over. Notably, not speaking about classical mechanics instead of quantum mechanics, but not only there. The Laplace operator is to be found in a very broad class of important, well, partial differential equations. Our next large topic after the multidimensional calculus will be, and also I hope the final one for this semester. I hope it in your for your accommodation, comfort. Well, it will be about differential equations describing technical systems, for example. But don't be worried. We will not be concerned with differential equations for functions of more than one free or independent variable. We will instead restrict ourselves to differential equations of one single independent variable. So it means we will be concerned with regular differential equations. Now I'm talking about something which appears in the partial case, of course, because all our fields have three independent variables. Now, importantly, also in Schrödinger's equation, but not only there, the delta, the Laplace operator, is in most of the cases applied to a scalar field, but not in this law which I just gave you. So this is a relatively seldom case where we apply the Laplace operator to a vector field. It's not a problem in any way, but it's just a little different. Okay, you understand? If I take delta phi, this phi would be placed here, 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 and here. So this would mean what I get is phi xx plus phi yy plus phi zz. And this is easily to be calculated. Always the same scalar term, twice partially differentiated for x, plus twice for y, plus twice for z. But now we apply this delta symbolic operator to a vector field, which means, in general, if I apply it to a vector v, it applies to all the components separately, you see. And there's nothing added up. So it means we have to take the first vector component and then build something like this. Take it twice for x, plus twice for y, plus twice for z, differentiated for x, y, z. And then the result is placed into the resulting vector at the first position. The same thing happens for second and third vector. It's not really complicated, but it's important to know. Okay, and we can test this. And this is what we finally do. We test whether rotation of f, which we just calculated, remember, this was our simple result, 2, 0, 0. If this may also be calculated the other way, as it's stated in this law. Well, and this is an interesting exercise just by itself, because it's just fun to look and see if we are able to take the gradient of the divergence of f. Of course we can. Look, this was our field f. Where was it? Here. We took a while ago, we took the divergence. Am I? Yes, I'm right. And here it was. Divergence of f gets us 4x, this interesting little term, 4 times x, interestingly. So remember, 4x. And now I take the gradient of, you see that this is a potential function itself. It may be interpreted as a regular, three-dimensional scalar field the specialty of this one is, of course, it just depends on x, but it might also depend on y and z. So the fact that it doesn't does not mean it's not a spatial field anymore. It's a scalar spatial field. And then now we take the gradient of this, let me say, potential function. Just for you not to be confused, what do we have to do? Remember, the gradient is just and simply, where is it? Here. It's just and simply this, sort of like this. Take whatever you have, partial for x, and then for y, and then for z, and build a vector out of this. So stay focused now. What I'm doing, I'm taking the partial derivative of this term for x, which is 4. And that's it. Then I take the partial derivative for y, which is 0. It doesn't depend on y. And also for z, again, is 0 because it doesn't depend on z. So what it means, I get a vector which holds, or which contains the elements 4, 0, 0. That's what I get. That's the gradient of divergence of f vector. It gets me a vector 4, 0, 0. And now you suddenly see why in this general rule, my so-called correction term, with the Laplace of vector field has to be taken, because this alone will not work. At the moment, we found that 2, 0, 0 should be equal to 4, 0, 0. This is not true, but we still have to take the Laplace of the vector field, and that's not even complicated. Also, look here. Why is it easy? I show you. Look back to vector field f, and remember what we do. We take delta, symbolic for the sum of the second partial derivatives of all variables. We do this, we perform this for the first, second, and third component of vector field f. Where is it? Here. Let's look here. Now let's just go. Partial for x, result is 2x. Keep in your mind. But we have to take partial for x and again for x. So xx. So first time I get 2x, second time I get 2. 2x gets differentiated to be 2, twice for x. And then I have to add the partial derivative twice for y of the same term, but it doesn't depend on y, so I have no more contribution. Plus even twice for z, no contribution. So this means that the Laplace of x squared is actually equal to 2 constant. Here, the same thing, but this time partial for x gets y, and again for x gets 0. So I need at least a squared contribution for a certain variable to have any contribution. So this gets differentiated away twice for x, and twice for y, the same thing. In the second step it disappears, and for z anyway, because it doesn't depend on z in the first place. So nothing. And this one, twice for x, twice for y, twice for z, no contribution. It means now we get another vector which, by not by chance, but for different reasons as before, will be the vector 2, 0, 0. You understood why? Okay. Take Laplace of the first one, Laplace the second, Laplace the third. We get a vector 2, 0, 0, and this has to be subtracted due to this rule, you know. And then in the end, we have vector 4, 0, 0 minus vector 2, 0, 0, which is vectors 2, 0, 0. Now it's the correct result as on the other hand side as before. So I think this was a simple but sufficiently significant example for all these connections between our important first order spatial derivative, let's say differential operators called gradient, divergence, and rotation. Thank you.